Okay, so last time we had begun a discussion of early Greek mathematics. So this basically started with Thales. So before I get into that, I'll say I'm sorry, guys. I meant to upload your first homework assignment, but I've had some tooth issues over the last couple days that have made it hard to do much of anything. So hopefully I'm not slurring my words too much during lecture because my face is kind of swollen. But anyway, I will get your first homework uploaded soon, and I'll send out an announcement when I do. So it won't be too long. Anyway, so from last time, I had brought up this Thales list of facts attributed to Thales. So just quickly, a circle is bisected by diameter. The base angles of an isosceles triangle are congruent. Three is when two lines intersect, the vertical angles formed are congruent. So these are the angles that we call vertical angles. The angle-angle side congruence theorem. So this is one of the shortcut congruence theorems for showing that two triangles are congruent. By definition, to know that two triangles are congruent, you would need to know that you would have three pairs of corresponding sides that are congruent, and then three pairs of corresponding angles that are all congruent. But that's too much info. In fact, you can get by with a lot less than that. So this says that you can get by with, so you might recall side, 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 and angle, side, angle. So angle, angle, side congruence theorem also works. It's actually a fact of angle, side, angle. So anyway, so he was the first to prove each of these things. The Thales theorem, that the angle subtended by the diameter of a circle is a right angle. What does that mean? So here's a quick illustration of this fact. So suppose that the general picture, let me bring this a little bit closer. Yeah, okay, so let me bring this a little bit closer. So here's the general picture of having 3 points A, B, and C on a circle. But imagine A and B are arranged in such a way that they are a diameter of the circle, right, instead of this. So for instance, like this. Okay. So imagine in this picture, A and B are arranged in such a way that they are opposite ends of a diameter. Okay, then this point C, no matter where it lies on the circle, the angle ACB must be a right angle. So this illustrates this principle here. Okay, so here we have AB. So this is a diameter. So A and B are endpoints of this diameter. Any point C that I draw in here on this circle, ACB is a right angle. So that's what is meant by this statement that the angle subtended by a diameter of a circle is a right angle. So subtended is exactly this situation. Okay. Now it turns out that actually in order to prove this, so Thales proved all of these facts, but in order to prove this last fact, he also needed to know, and this is called the Thales theorem. There's another theorem called Thales theorem that I'm going to mention also that your textbook doesn't mention. So in order to prove number 5, he also needed to know that the interior angle sum of triangles sum to 180 degrees. So he also needed number 6, which is the sum of the angles in a triangle is 180 degrees. We use degrees here in a way that maybe the Babylonians would have, right? So that's the idea, right? So the Greeks phrased this differently. The Greeks said the sum of the angles in a triangle is equal to 2 right angles. So the sum of angles in a triangle is 180 degrees. Again, the Greeks would have said is equal to 2 right angles. Okay. So, as I mentioned last time, what is the big deal about this list of things? Well, because Thales was the first to prove these things. Okay, this was the first example in history of mathematical ideas being proven, right, via mathematical proof. Okay, so these were the first times that facts were rigorously established using mathematical logic. Okay. Now, all of this list, as I said, were actually known to both the Egyptians and the Babylonians, but Thales was the first to prove them, and Greek mathematicians were the first to prove. Okay, and that's why this is a big deal. Another aside here, so also another theorem attributed to Thales, which is what I've always heard called the Thales theorem as well. It's the following. So it has to do with parallels cutting lines they cross in proportional segments. So this is another Thales theorem. So parallel lines cut lines they cross into proportional segments. So what is meant by this? Well, here is an example of dividing a line segment into equal parts using the construction of parallels. Okay. And this example of using this Thales theorem to show that the ratios here, so consider I have a triangle here. I have a line, L, that is parallel to this base, BC. So this line L crosses the segments AB and AC at points P and Q, and it's parallel to BC. Okay. Now, the Thales theorem in this case would say that the segment AP divided by PB is equal to AQ divided by QC. So these are the lengths I'm talking about. So the length of segment AP divided by the length of segment PB is equal to the length of segment AQ divided by the length of segment QC. This is what is meant by this proportionality. So this is the Thales theorem in a triangle. Okay. So it turns out that this is extremely important for being able to introduce algebra into geometry, or rather to introduce algebraic operations through geometry. So that Thales theorem is essentially all that is needed in order to come up with geometric constructions of multiplying and dividing line segments. Okay. All right. It's important to note this distinction of ratios, and the Greeks were very much interested in dealing with ratios of line segments whenever possible. In fact, they came up with a very, very sophisticated way of dealing with these ratios. That is, it's book 5 of Euclid's Elements, is this theory of proportions, which was due to, I believe, Eudoxus. And I will talk about later, because it's very interesting, why they were so worried about these things. There's a very specific reason they were worried about this, and it's because they were worried about irrational quantities, okay, that we'll talk a lot about. So anyway, continuing on with Thales. So again, you know, while all of these facts were known to both Egyptian and Babylonian mathematicians, the Greeks were the first prove these. Okay. And so this list of facts attributed to Thales, these were all proven rigorously. Okay. So this is that list is the main contribution of Thales to the dawn of Greek math. Okay. And this is important because it immediately led to the next big contributor to Greek math, which was Pythagoras. Okay, which no doubt all of you have heard that name before, so we'll spend a good bit of time talking about Pythagoras. So before that, however, you may have heard Thales named in another context, and that's in philosophy. So philosophically, what was Thales known for? So Thales' philosophy was summed up with a statement that's pretty widely attributed to him, that all is water. Okay. All right, all things are water. Okay, so what did Thales mean by this? So the textbook goes into a description of, for instance, in ancient cultures, and even today we still have the remnants of this. There were count nouns, okay, and there were nouns that were not count nouns. So what do I mean by that? So for instance, it makes sense to say that you have 3 rocks, right? 3 pebbles, or 5 cows, or 10 chickens. Okay, but you wouldn't really say that if you were describing something that wasn't as amenable to counting in this way. So the example the textbook gives is butter. You wouldn't say 1 butter, 2 butter. And so, some nouns are mass nouns and some are count nouns. Of course, there are some exceptions, various words. So the textbook mentions rice, right? You wouldn't say rices. Rice is an example of there's a discrete quantity of rice, but you call it rice still. You wouldn't say rices or X number of rices. So the idea is this is a really crude way of thinking about the notion of discrete versus continuous. So what is the main thrust here? So the idea that the visible universe is discrete, right? Discrete meaning that there are these finite, in some sense, units, these finite things, okay, that make up the universe. So later we talk about Democritus. We will, discuss the notion that everything is made up of these indivisible atoms, right? Was one idea. The Pythagoreans thought the exact same thing. So in the discrete camp, you had Pythagoras and his followers. Pythagoras and his followers believed that all was number rather than all is water, and we'll talk about that a bit later. But the idea still was that there were these like indivisible blocks that made up reality. So another believer of this is Democritus, right, and his atoms. All right, so Pythagoras, all is number. And really what was meant by that was ratios of numbers. So everything could be built out of these ratios of whole numbers. Democritus is all is atoms. Right. Okay. Versus the continuous camp, which is the idea that there's some continuous substance that is kind of the true thing that makes up reality. Now, don't focus too much on the claim that there is a single substance for which this is the case. That's not really the main idea. The main idea here is the notion of a continuum versus these discrete objects. I mean, it's actually still a very hard thing to discuss, even now, philosophically. If you look at the standard model of physics, the standard model of physics posits that we live essentially on a mathematical object. Okay, so some sort of what's called a manifold, or some sort of manifold-like space. Now you could say, okay, well, do we live on a literal mathematical object, or do we live on something that this mathematical object approximates? That this just adds, more more complication to it. But the idea still is that whatever this object that we're talking about, whether it models it or not, is a continuous object in a real rigorous sense. Okay, and so in a lot of ways, that means that essentially the standard model of physics tells us that we live in a continuous universe, and lots of the things that you might think of, just in the way that the world works, lend themselves to, they feel more continuous than discrete, right? So you imagine whether or not a given problem is like amenable to computation, right? So this is, how do you translate something continuous into the world of the language of a computer, which deals in discrete things. But that being said, there's a lot of very deep things going on, especially in theoretical physics, and its interface with math, that there are these combinatorial objects that show up in strange ways that make it almost seem like maybe the universe is some kind of object that's not really quite continuous. Maybe it's some kind of weird graph or something. So this is not really the point of this discussion. This is mostly just to say that this argument of discrete versus continuous, what's the true nature of reality, is very much not really settled. Okay, and when we get to Plato, you're going to hear my rant about how when I first heard Plato, I thought like, oh, this silly like ancient Greek philosophy, like it's just too outdated, and it's it just doesn't apply at all. It gets everything wrong. And then I thought about it a lot in grad school, and now I'm like a full-blown Plato devotee. Plato was right, basically, is my belief. So anyway, we'll talk about that. I will rant at you plenty about that soon. But anyway, on the continuous side of things, you had Thales, which says that all is water. Okay, and what he's saying there again is that there's this continuous substance that is the nature of the universe. And there was also Heraclitus, which you might have heard of. He's oftentimes called the weeping philosopher. He's the philosopher that said, you can't step into the same river twice, right? Everything flows. So this was Heraclitus. So Heraclitus didn't believe that everything was everything was water. He believed everything was fire. So all is fire. Okay. Heraclitus, so Pythagoras was from 570 to like 500-ish. Democritus was in the 500s as well. Heraclitus was roughly 500 BC, and Anaximenes was 550 BC. So Anaximenes is another. Okay. Who said all is air. Okay, so in a sense, they're almost covering all of the, these Greek primordial elements, right? Like earth, water, fire, and air. Almost with a little bit of wiggling, you could say that they're basically covering. Well, you could either say they're forming Captain Planet, or they're doing some kind of approximation of the states of matter or something. So anyway, in fact, there's been a ton of time devoted to discussing why Thales picked water. So I believe that your textbook says that Marxist historians suggested that he picked water because his city, so it's Thales of Miletus, so his city Miletus was a maritime power, and so that's why he had this affinity for water. Anyway, Anaximander was another in this continuous camp, and his substance was kind of a more ethereal substance. He just called the infinite. So anyway, that is a discussion we'll delve into again in a little bit. So anyway, that is Thales and his contributions to math. So that list had been attributed to Thales since the Pythagoreans, I believe, for almost all of those. So that is the evidence that it was Thales that did this, because this was known prior to the Pythagoreans. And his contribution to philosophy is this statement, going against the notion of a discrete universe. So, what I wanted to talk about next was Pythagoras and his school. So, Pythagoras and the Pythagoreans. So, they were the Pythagoreans were essentially kind of 50% a political party and 50% a religious cult. But part of their religious cult activities, of course, was engaging in mathematics. In fact, the first use of the word mathematics came from the Pythagoreans. Its more modern definition, it was due to Aristotle, but the Pythagoreans were the first to use the word mathematics because the inner circle of the cult were called mathematicians. So Pythagoras was born roughly 570 BC, died 500 BC. What's known about his life is he was born in Samos, which is a Greek island off the coast of Turkey. And according to ancient sources, he traveled and studied in the Persian Empire. And of course, at this time, if you quickly check your years, at this time, the Persian Empire had absorbed the Babylonians by this time. So the Persian Empire stretched all the way from modern-day Turkey, to from modern-day Turkey all the way to India, right? All the way to the Indus Valley. And so the Persian Empire was huge. So he studied in Persia. From Persia, it is likely that much of Babylonian mathematics he was exposed to. So we knew from the clay tablet, the Plimpton 322, the Babylonians knew the Pythagorean Theorem and knew how to compute Pythagorean triples, right? They even knew this method of generating Pythagorean triples. And so it is likely, it is at least possible that Pythagoras actually learned the Pythagorean triangles from the Babylonians, as he studied in Persia. And anyway, Pythagoras also studied under Zoroastrian priests. But it's been suggested that because he was a vegetarian and he believed in reincarnation, that it's likely that he was actually more influenced by a Hindu tradition the Indian influence from Eastern Persia. So anyway, around 525 BC, he moved to Croton. So studied in Persia. Moved to Croton in roughly 525 BC. Croton was a Greek colony in southern Italy. Okay, so this is in southern Italy. At the time, southern Italy was mostly Greek colony city-states. So this was southern Italy. And it's here that he founded the Pythagoreans. Okay. So this is called the Pythagorean Brotherhood. So he founded the Pythagorean Brotherhood. Okay, in Croton around this time. Okay. So it was about 50% a political party and 50% cult. So about 50% political party and 50% cult. So this cult aspect was where the mathematics came in. So the inner circle were called mathematicians. And the root word mathematics, so this as a word was first used by the Pythagoreans. So apparently the root word of math is an Indo-European word, or is related to the Indo-European word mind. Okay. Now, the modern definition of mathematics is due to Aristotle, which I'll mention when we get to him. But this is where mathematics came from. Yes, Benz, that's true. That the Pythagoreans, the Pythagorean cult is basically who named. They are the ones who named the field, more or less. So yes, that's true. As I mentioned previously, one of the main belief of the Pythagoreans. So the Pythagoreans, and really Pythagoras himself, the Pythagoreans, maybe I should say that to make the distinction. It can, as we'll see, it can be hard to make this distinction because all of the discoveries of the Pythagoreans were attributed to Pythagoras, even when it might have been due to his followers. In fact, a lot of these discoveries happened later on after Pythagoras had already died. Anyway, Pythagoras taught that all is number. Okay, and that seems a little more innocuous than what they actually were claiming. Basically, they were claiming that everything that you could dream up mathematically could be done in a way that could be reduced to whole numbers and ratios of whole numbers. Okay. So here's the translation of all is number. Maybe I'll do that on the next page. So the translation, all is number. What this really meant is everything can be described by whole numbers and ratios of whole numbers. Okay. So what this means, for example, so given some unit length, so given a length, say, imagine a length of rope or something that you are specifying as a unit, right? Because the ancients understood that a unit of measurement was simply a common thing to compare to, right? So it wouldn't make sense if I was using some type of unit, someone else is using another type of unit. If we wanted to make comparisons, I would need to know I would need to know a way of comparing those two units in order to understand the the length, right? And so the idea of units in the first place was just having a common way of comparing lengths. And so you imagine some stretch of rope that you call your unit length. So once you've established your unit length, the idea was that, say, every line segment, right? Every line segment, so the length, so this is the claim, the length of every line segment is a whole number or a ratio of whole numbers. So this is a Pythagorean belief. Okay. As we will see, and as you probably already know, this isn't the case. Right? There are certainly lengths that unfortunately cannot be expressed in this way. They're neither a whole number nor a ratio of whole numbers. Okay, and you don't have to look very hard to find these. In fact, the Pythagoreans did find them. Okay, so note Pythagoreans discovered this was untrue, but Pythagoras seems to have never known this. Okay, and there's an anecdote about this that I'll say now and then I'll repeat, which is that the first Pythagorean, supposedly, that discovered that this boxed statement is false was thrown overboard and drowned while the Pythagoreans were, because this discovery was supposedly made while the Pythagoreans were on a ship. They were on a journey traveling to somewhere in the Mediterranean, and one of them was like, oh, I believe that I've shown that actually there exists a line segment whose length is neither a whole number nor a ratio of whole numbers. And the story goes that he was thrown overboard immediately. Okay. So, again, and I'll mention that story a lot, whether or not it's true or completely apocryphal. I think it's a funny story, so I'll mention that again when we talk specifically about what was discovered. Okay. So then, philosophically, before I get into some of the mathematical achievements, philosophically, what were the achievements of the Pythagoreans, or what were the kind of the things they were known for? So philosophically, the Pythagoreans well, really, Pythagoras himself was the main driver of this fact specifically. They held 10 to be the holiest number. Okay, why was 10 a divine number? Okay, so there's a couple of reasons. So one, the symbol of the Pythagorean cult was this star. Okay, this is the Pythagorean star. Okay, and if you count the vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This thing has 10 vertices, okay? And so with 10 vertices, you could come up with this Pythagorean star. Okay. Similarly, 10 is the fourth triangular number. Okay. So 6 is a triangular number, but it's also a perfect number. 10 is a triangular number. What's a triangular number? If you imagine taking that many objects and arranging them or trying to arrange them into an equilateral triangle, equilateral here, we're measuring the side lengths as the number of objects in a side, then you can do this, right? So you could do it with 6, you could do it with 3. 1 is just considered not a triangular number, so we would have 3, 6, 10, and so on. 10 is the fourth triangular number. Okay, and this was considered very, very nice by the Pythagoreans. Okay, so as your textbook states, while the Pythagoreans attributed basically every discovery to Pythagoras, there's not a single theorem that was due to them that we can safely say was actually due to Pythagoras. So there is no that we can definitively say was due to Pythagoras himself. So rather, every discovery of the Pythagoreans was attributed to him. Now, while that's true, it's also good to note that there's not... This isn't to say that there's anything that it was due to the Pythagoreans that we think that Pythagoras could not have shown or wouldn't have been able to show. It's just a question of there's no hard evidence that it was due directly specifically to him and not some other Pythagorean. Okay. And so, in fact, there's so supposedly, here's an example of this. So this was due, I believe this is noted, Introductio Arithmetica. So in Introductio Arithmetica. So this was written in 100 AD by Nicomachus. Okay, so in a preface to this, in a preface to this, which was written in 300 AD by Iamblichus. Okay, Pythagoras supposedly knew of an amicable pair. I'll explain what that is in a second. So the amicable pair in question is 220 and 284. Okay. So what is an amicable pair? An amicable pair is it's two numbers, two natural numbers, two whole numbers, such that if you consider the sum of the proper divisors of each, the sum of the proper divisors of each equal the other number. So if you took all the proper divisors of 220, so proper divisors means not 1, not 2, not 220 itself. So you took its proper divisors and you added them all together, you get 284. If you took the proper divisors of 284 and added them all together, you get 220. That's what an amicable pair is. Okay. And so, supposedly you knew of an amicable pair, and supposedly when he said all is number, someone said, well, then what is friendship? And Pythagoras said friendship is the same as 220 is to 284. Okay, this is the story. Now, whether or not Pythagoras actually knew this, note how much later this account occurs, right? Whether Pythagoras actually knew this or not is unknown. Okay, but this is the kind of things that were attributed to Pythagoras, and there's just no way of knowing whether or not He actually knew those things. But again, it's not outside the realm of possibility, for sure. And so, what were some of the things attributed to what were some of the things due to the Pythagoreans? We definitely know that the Pythagoreans were responsible for these things. Let me get some more paper. So, achievements of the Pythagoreans. Okay, so what are some of these things? Of course, the theorem of Pythagoras. Okay, that's number one. Okay. They also were able to prove the converse. Okay. Now, actually, while again, we know that the Babylonians knew about the Pythagorean theorem. The question, right? The question that's totally known is that this wasn't proven, right? The Pythagorean theorem was not proven by the Egyptians or by the Babylonians. And the Pythagoreans definitely came up with a proof of this fact. And in fact, the proof that they came up with is likely the proof that shows up in Euclid's Elements. So it's impossible to discuss geometry in a sensible way without mentioning Euclid's Elements, even though in our time scale here we're a couple hundred years before they were actually written. Okay, but nevertheless, it is absolutely impossible to reasonably discuss geometry and, where geometry was headed without discussing the elements. And we're going to spend a lot of time discussing the elements here. But if you want to see this proof of the Pythagorean theorem that was due to Euclid, there are tons and tons of proofs of the Pythagorean theorem. In fact, there's an interesting proof of the Pythagorean theorem that was proven by a president, a U.S. president. Believe it was Garfield. Let me look really quickly. I think it was Garfield. James Garfield's proof of the Pythagorean theorem. It is interesting because it uses the area formula for a trapezoid to do this. So there's tons and tons of ways of proving the Pythagorean theorem. And in fact, there's plenty of novel ways that it's still yet to be discovered, I'm sure. So there's lots of very nice intuitive ways of doing it. This is one of them, and this is due to the Pythagoreans. So the statement of the Pythagorean theorem, of course, is that for any right-angled triangle, the sum of the squares on the two shorter sides equals the square on the hypotenuse. What is nice about this proof is that we are used to using square in the sense of you take a number, raise it to the second power. We call that a square. Why? Well, we call it squaring a number because we can literally construct the square, right, on those sides. And if I call this side length A and this side length B, what's the area of my light gray square and my dark gray square? Well, this would be A squared. This would be B squared, right? Okay, and so the point is that this C squared can be made up entirely of two rectangles. The rectangles, the shaded area, has exactly the same area as these squares. And so C squared is equal to A squared plus B squared. You can just see it in the square. So this is the proof of the Pythagorean theorem that the Pythagoreans came up with. If you want to see how this proof goes, the steps in the proof, here it is. So you start with the light gray square and you color half of it here. Okay. Then you can pass to this half. This is basic facts about this triangle and this triangle having the same area here. This is not hard to reason through. And then you can pass through, if you draw this perpendicular here, you can pass through to this triangle, and from this triangle to finally this. And of course, you didn't have to start with half this square. You could have started with the whole thing. And if you did, you would have gotten that square is exactly this rectangle. And then you could do the same thing for the other side. Okay. So this is the proof of the Pythagorean theorem that the Pythagoreans actually came up with. So they were able to prove the converse. What is the converse of the Pythagorean theorem? Oh, I'm blurry. So the converse of the Pythagorean theorem just states that if you have a triangle, right, that has these three sides a, b, and c, such that a squared plus b squared is equal to c squared, then that triangle is a right triangle. Okay. So that fact is intimately related with that triangle being a right triangle. Okay. All right. What else did they talk about? So another achievement. Perfect numbers. We will talk about this next time. So perfect numbers. They actually came up with ways of generating perfect numbers. So we'll talk about that next time. What's a perfect number? Perfect number is a number whose proper divisors add to it. All right, so 6, 1, 2, and 3. 1 plus 2 plus 3, that's 6. Okay, so, and 1, 2, and 3 are the proper divisors of 6. Okay, what else? Well, regular polyhedra, which we will also talk about next time. So these are the so-called Platonic solids. Okay. They also discovered, much to their dismay, the thing that absolutely annihilated their central belief. They discovered the irrationality of the square root of 2. We will discuss this a lot. Okay. Okay, so these are the big things. So they had some other achievements I'll list here in a second. The irrationality of the square root of 2 is particularly important because what this means is that the square root of 2 cannot be expressed as a ratio of two whole numbers. Now, how would you show such a thing? By contradiction. You would assume that it could and then arrive at a contradiction. Okay. And so while they knew that it couldn't, so they knew that it couldn't be rational. Rational means it can be expressed as a ratio of whole numbers. So it couldn't be rational. They also they approximated it. Now they approximated it, but they did not approximate it to as good of a degree as the Babylonians. So the Babylonians actually approximated square root of 2 more accurately. I believe that's true. I'll have to check actually, but I'm fairly certain that's true. Okay. What else did the Pythagoreans discover, or what else were their other achievements? So they investigated means, meaning the relationship between the average of two numbers, so a plus b times 1/2, the geometric mean, which is square root of a times b, and what's called the harmonic mean, which is 2ab over a plus b. Okay, so the relationship between those things. Okay. They also discuss what are called figurative numbers. Okay, which I'll talk about a little bit next time. Okay, and what is nice, of course, is that there were proofs for all of these facts. Okay, so everything listed here was accompanied by proofs. The irrationality of square root of 2, there was a proof that square root of 2 is irrational. Okay, there was a proof for a formula generating some perfect numbers. Okay, there was the proof that I showed earlier of the theorem of Pythagoras, right? And a proof of its converse. Okay, there was a proof of regular polyhedra. In particular, I believe they discovered the dodecahedron. So they discovered the dodecahedron. Okay. All right. Okay. So I will go over some of these achievements in detail next time. So specifically, next time I'll cover their achievements on perfect numbers and regular polyhedra before moving on to the crisis that was caused in the Pythagoreans by the irrationality of square root of 2. This is called the crisis of the incommensurables. So square root of 2 was said to be incommensurable. Okay, and I'll explain what it is that meant. Okay, so I think that's all for today. I will see you all on Friday. Before Friday, I'll post your first homework. I know I've been promising it since last week, but I'll actually get it posted, and I'll let you know when I do. I'll send out an announcement. So anyway, that's the deal. So I'll see you all on Friday.